We're just going to do a bit, I said we were going to have a bonus quiz today, but actually we'll do that Wednesday or Thursday. What we should do is have a bit more of a review of the work we did last week. We're going to go into some detail here in volcanoes. Toward the end, we're going to talk about why igneous activity occurs where it does in a plate tectonic setting. We've touched on that a bit when we talked about how we actually get the solid Earth to melt, those three different ways: decompression, or putting water into the system, or just a transfer of heat. But we didn't really talk about where that happens. So we'll go into the plate tectonics is the theme that underlies all the stuff that we do in this semester. Last semester, if you did Earth systems, that theme was surface processes and change and global change. The theme here is plate tectonics. So we'll do that toward the end, but I think it would be good. This links in with the prac work you're doing, and it's the kind of thing you should be able to do and answer on the upcoming lecture test that we'll have that covers this material. So there are two handouts. If you didn't get them, just run up and grab them here, go to the back and get them. And you reprobates in the back, if you didn't get one, you'll have to run down quick like a bunny. One of them is 2 pages. Two sheets stapled together. The last is just a crossword puzzle for fun, so I won't talk about that again. The other one, though, the other one has this drawing of rock classification on the front, and then on the back, oops, I don't like this because I have to keep going back and forth. On the back, this is a table that's all filled out. There's nothing for you to do here. And this is something that will be good for your study and relates to the material we'll be doing at the end of this week. But it gives plate tectonic setting, the process of forming magma, because remember the Earth is solid, so we have to form molten rock somehow, the process of doing that and the location, and lavas that erupt, and if they do, why do they erupt at that spot. So you can see that it does divergent boundaries, convergent boundaries, and hot spots. We're going to go over all those, but that puts it all into a nice table. What was I going to say about that? Derek talked about this a little bit, but we say these lecture tests aren't cumulative, that they don't specifically test you on material from the previous part of the course, but certainly when we talk about magmatic processes and plate tectonic settings of igneous rocks, it's just kind of assumed that you've assimilated that material about plate tectonics from the first part of the course. Okay? So don't forget about that part of the course. It ties in everything that we do. So that's just kind of for reference. But let's go ahead and just do a bit of work and make sure that you understand this diagram. This is another way of looking not so much at magmas now, but at the rocks that are produced from magmas. And there's a similar diagram to this in your reference book for your mineral and rock ID work, the big thick handbook. There's a couple that are similar to this, in fact. So just I explained it in text, so ignore me and read if you prefer to read yourself, but it's got rock names listed across the top, both the aphanitic or fine-grained or extrusive version, those words we all use as being synonymous, or the intrusive, coarser-grained phaneritic. Could still be quite small grain, but the point is you can see the grains with your hand lens. So that goes across the top. The percentage of minerals shown by volume going up from 0 to 100%. So any given rock should have 100% of everything in it in total. So the individual mineral component should add up to 100%. What else does it give you? Plagioclase shows the continuous series range between calcium-rich and sodium-rich. And then just a little fact here that the mean composition of continental crust, so the average composition of the crust that we walk on is andesitic or dioritic. So not completely felsic, not completely mafic, but the mean composition of oceanic crust is basaltic or gabbroic. So I was going to write this, but this diagram does also show you that felsic is on this side, mafic is on this side, and then ultramafic. So, starting with question A, B, let's just do A, B, and C. Let's just do those to warm you up a bit. Take a couple of minutes to answer those, and let's see how you go. Okay, are we pretty happy that plagioclase feldspar is probably the most abundant in average continental crust? Thumbs? Yep. So if all the plagioclase in the earth, I always say if all the feldspar in the crust disappeared, we'd fall to the mantle. So the way you read that is you just take, let's say, you're going to put your average right down the middle. All those minerals have to add up to 100%, and there's a lot of plagioclase feldspar in that spectrum. If you do the same for oceanic crust, I think that was the next, so that's plag. If you do the next for mean oceanic crust, well, depending on where you put this line, either pyroxene or also plagioclase feldspar. I only just said broadly basalt or gabbro composition, but one of those two. So pyroxene. Oh, and I don't have, oh, there you go. I don't even have the possibility of plagioclase there, so you wouldn't circle that one. Okay, this is a hard question. So we said that the mean composition of the, sorry, senior moment. Am I recording? Yes. Whew. The mean composition of the complete continental crust is andesitic. So if you took a whole column of continental, if you took all the continental crust in the world and ground it up and analyzed it, it would be andesitic. That's the top part, the middle part, the bottom part, everywhere in the world. But this is telling you that the deep crust is more mafic than andesitic. So if this is crust, continental crust, this is deep crust, and then it wants to know, would plutons in the shallow crust then be more mafic or more felsic than the deep crust? Well, thinking about this balance, which way do I have to go to balance out? Do I have to go that way or that way with the upper crust? Do I become more felsic or more mafic in the upper crust? Felsic. It becomes more felsic. That kind of makes sense, really, if you think about it, because always remember that when you partially melt something, you always make a product, a partial melt product, that is more felsic than what you started with. So a lot of the upper crust is just created by the process of recycling the lower crust, so it's always going to be more felsic than that. So kind of balancing this as a ruler, this would be upper crust on this side, average continental crust, and deep crust. Okay? D. Let's just try all the rest of them. I'll just take 2 or 3 minutes for that because there's a few more. For letter E, I'm actually looking for the name of the rock that would be formed, the name of the extrusive rock that would be formed after that event happened that's described there. So not what kind, but the actual name of it. This is really a key place where people screw up on the lecture test because they read too quickly or they're not paying attention and they give me some mineral name when I'm actually asking for some rock name. So you might be looking at that one, and the answer is, for letter E, a granite batholith is melted completely, which isn't going to happen. But if it did, the magma gets erupted, what kind of extrusive rock would that be? So no change in the bulk composition of what you started with, which doesn't happen. We've talked about partial melting, but just pretend that the whole thing melts. So if you melt an entire granite and then place it on the surface, what is the rock that it becomes as an extrusive rock? It becomes a rhyolite. But, you know, some people might panic and say, potassium feldspar, because they're thinking, all right, there's going to be a lot of potassium feldspar in that rock that comes from completely melting a granite. So don't mix up your mineral names with your rock names when you give answers on your lecture test. Not that this is all about how you're going to do on the lecture test, but these worksheets are to give you a feel for the places where you can mess up, and it gives you a feel for the kind of stuff you need to know. So question that we kind of skipped question number D because this young man got me to thinking about E, but if the mantle is, especially the upper mantle, is mostly peridotite, could we melt continental crust and get peridotite from it? No, that's never going to happen. You never get more mafic stuff from more felsic stuff. So the answer to D is no. Partial melting of typical continental crust will just give you even more felsic material. Okay, we did E, F. All else being equal, blah, blah, blah. Okay. We did viscosity, and I think you did get your heads around it, and we did the little role playing. Always think about the people who got the candy. This is giving a statement that more felsic magmas tend to be more viscous. So now in your head you have to say, okay, felsic. Is basalt felsic or is rhyolite felsic? So which one of those is a more felsic magma? And you can look on your chart if you're not sure. Rhyolite. Like I wouldn't even, this chart will probably be something like this will be somewhere in the test so that you actually kind of, you kind of have the answers, you just have to not panic. So yes, rhyolite, that chemistry is more likely to lead to explosive volcanism. We talked about how the gases can get trapped in the viscous magmas rather than in the low viscosity magmas. How about G? Ancient deposits of komatiites. Well, this question is kind of like question E in a sense. So the composition of the upper mantle was no different, and we're talking ancient, we're talking billions, 3 to 4 billions of years old, these komatiites. They are the equivalent of peridotite. And the upper mantle was peridotite then as it is now. So we don't have komatiites are incredibly, incredibly rare now. But they're the source of a lot of diamonds. So getting magmas from that deep is very rare. But, okay, having said that, in the past, billions of years old, they're the extrusive equivalent of peridotite. Have a look at your chart. So, in just 1 or 2 sentences, how could you possibly, why would we maybe have had komatiite back in early Earth history, but don't have any now? Something we didn't really talk about. The Earth is still radiating heat. There's still radioactive decay. It's still, the outer core is still molten, and it still is a heat source for the Earth. But the Earth is cooling down. The geotherm, remember when we plotted that geotherm, the temperature through the depth of the Earth, and it was a certain curve. That geotherm, at all given depths, that temperature was higher in the early Earth history. We actually think that plate tectonics operated at a much more rapid rate. The Earth was cooling itself off through mid-ocean ridge volcanism, so we think that the structure of the Earth was to have these microplates all over the place instead of the big plates that we have now, and massive amounts of outpouring at mid-ocean ridges, which is a little bit off the track. But with a higher geotherm, it's possible that we actually we're able to completely melt parts of the mantle to produce these komatiitic lavas, so that they are, in fact, that there was complete melting when the Earth was very, very hot in certain circumstances where we would perturb the underlying mantle structure. So we don't see this anymore at all. It's the same idea that in plate tectonics, in subduction zones, where I talk about how we drive off the volatiles into the overlying wedge, and that's how we get partial melt. Early Earth history, for those scientists who are trying to argue that plate tectonics happened early in Earth history, it's argued that it's actually the subducting slab itself that would be melted and produce volcanic arc magmas and lavas. The fate of those subducting slabs is a big topic of research in geophysics, because where do they go? Think about all of that oceanic crust and upper mantle, that lithospheric plate going down into the mantle. Where does it go? There's discussion about, in deep earth seismics, about evidence for subducted slab graveyards where it might sink all the way down to the mantle core boundary and just kind of hang there for a while. Fascinating area of research. But the point here is that the Earth may have been, and the Earth in fact was much hotter. Okay, so that was just that. All right, we might just start. So, well, let me just show you here. I'm not going to do this, although I promise I will post these answers. And for the ones we did last week, I just need to sit down for a few minutes. So this other handout, I'm on the second page. This is kind of a similar diagram again. It's interesting how many different ways that you can express this. What this diagram does, again, it gives felsic to ultramafic across the top, gives the texture along the bottom, along the side here now, though, and I'll just put them together just to show you that they're the same thing. How's that? Those are the same diagrams in a sense. They're giving you all the same information. They're giving you texture. Here, textures up here. They're giving you names of rocks of those ranges of compositions, both extrusive and intrusive, which it divides up here, and then Here it gives a rough guide to the minerals that are present in those different categories of rocks. You might be thinking, well, why is the rock test so hard? If I think I've got this rock, and I think it's a granite, then I'm just going to say, on the test, I'm going to say, 25% potassium feldspar. Oh, what's that? 35% quartz, 10% plagioclase feldspar, and 5% biotite and 5% amphibole, because I'll just read it off that chart, and I think it looks like a granite, and it looks like the photos I have. Well, you know what? You'll probably be almost completely wrong there. Probably that granite's not going to have any amphibole. It'll be something up here, and you'll get the percentages way wrong, and you'll include minerals that don't even exist in it, and you really won't get very good marks. So it's definitely good to understand those diagrams, but look at the range. Look at the range of granite composition. So I can give you a granite that's way over here, or a granite that's way over here, and you'll give me quite a different mineral assemblage based on what you actually observe. So it's really important that you say what you see in the rock and what you observe. This is great to help you if you think, oh, what's that dark mineral? What might it be? Oh, yeah, it's got to be biotite or amphibole. So that's a great way to help you clue into what it might be if you think you're looking at a granite-type rock. And then being able to classify that the mineral assemblage is only one part of the rock test. You also have to describe the texture, which is about, I've got to put my glasses on, which is about this sort of stuff here, and using those terms appropriately. So this is a great guide, though, and it's good to learn to be able to read these diagrams. So all of these questions are pretty much the same sort of thing that we just did, so I won't go over those with you. But what we can take a few minutes more to do, just for a little bit more review before we get into volcanoes, is give a try here to the front page of this. All you have to do here, and I won't give you much time at all because I think you'll be pretty quick at it, is read the statement and decide if that applies to either one of those types of rocks. This is intrusive and extrusive. Good to get used to all the synonyms. And see if that statement applies to either of those rocks. So may form from basaltic magma. Well, as soon as you see basaltic, you think, oh, that's extrusive. So yes, no. So that's something on the surface. Form at the Earth's surface. Well, that's the whole difference between those two. Okay? So try the rest of those. Again, just for a minute or two, and we'll see how you go. That's another really good point that you must get into your head. I'll just put it up. So in the rock work that you're doing, we keep saying only describe what you can see. So some people that have gotten to that, that basalt that has the holes in it, you can't see any minerals in that basalt. So you wouldn't want to describe to me, I'm just going to put this up for a second. So you think you've got a basalt, it's got a bunch of holes in it, some vesicles. You don't want to be telling me what minerals are in that, because you can't see any minerals in that basalt if it's the one that we're working on in the box. There's nothing you can see. So in the mineral composition part, you put 100% can't see it, or too fine grained, or however you want to word it. You wouldn't want to tell me, oh, and this gets like 0 marks when you do this. You wouldn't want to be telling me, oh, my basalt, which I can't see anything of, has, 50% plagioclase and 2% amphibole and whatever that comes to, 20% pyroxene and 10% olivine. That's like 0 marks if you're telling me you can see that in your basalt. But that's the question of what you can see in it. And in the thin section, you could see that. The thing is, the extrusive rocks and the intrusive rocks that are companions have exactly the same mineral composition. They're just too fine to see in the extrusive rocks. So they might, so when I say exact, it's got to be exactly, in that line. So if that is your rock and you can see minerals in it, they're going to be in those percentages. If you can't see minerals in it, well, if it's got the same chemical, this is about the chemical composition. If it's got the same chemical composition, it's going to have those minerals in it. You just don't want to be saying that on the rock test because you won't be able to see them. So yes, an extrusive rock can have as many dark-colored minerals as an intrusive rock if they're both mafic, if they're both made up of magnesium iron-rich bits, minerals. Okay, that's really, really key to get that distinction. So I'll just run through some yeses and nos. I'll do it fast so if I get any wrong. Have texture, yes, yes, must all have texture. Even if it's fine-grained, it's a texture. It's a texture called aphanitic. Yes, no. Granite is an intrusive or a plutonic rock, yes. Rhyolite is the extrusive equivalent. Form as a result of partial melting. I'm going to change that for next year. Yes, yes. Present at the Earth's surface only after erosion. The whole point about extrusive igneous rocks is they solidify at the surface, or if they're pyroclastic, they're erupted. So, no, they are there emplaced. They might be emplaced and then buried and then eroded later to be seen at the surface, but they were originally emplaced at the surface. But yes, that's true for the intrusive. Yes, they all contain minerals, just whether you can see them. Dark-colored examples have low silica content. Yes, that's kind of random, but yes. We okay with those? Okay, just 2 more. Yeah, we're doing fine. So check out this diagram at the left. And it wants to know what minerals are removed, what elements. So what elements, like in the periodic table elements, are removed from this particular magma during early fractional crystallization. So it's a magma, it's all molten. Early on, it's going to start to form minerals. So what elements will be removed to make what minerals? Well, let's say first, what minerals are we going to form as we start to cool down a magma? If it's a primary magma with a whole range of, if it's come right out of the mantle and it starts to cool, what's the first mineral we'll form? Think of Bowen's reaction series. There's the discontinuous side of Bowen's going from olivine, pyroxene, amphibole. There's the continuous side going from calcium-rich plagioclase to sodium-rich plagioclase. So the highest temperature minerals we're going to form are olivine and calcium plage. So the stuff we're going to remove to do that, we're going to remove a lot of iron and magnesium and iron. calcium. We are also going to move silicon and oxygen and aluminum out of there, but those proportions of silicon to oxygen will not be as high, the ratio. We are going to take out more silicon relative to oxygen as we go on and on. So if that's like a melt from a peridotite, first thing we do is make olivine. We make calcium plagioclase. We don't take out any sodium or potassium at this point in time. That's a much lower temperature crystallization phase. So, what's the next question then? All right, this is then suggesting that we've just made olivine at the very first. So it's taken the same magma. We've fractionally crystallized some olivine, and the question is, what effect does that have on the overall proportions of the remaining elements, all of those in the magma? Well, those are all elements that are found more in felsic minerals. Sodium and potassium are found more in things like potassium feldspar or the low temperature plagioclase. Silicon to oxygen ratios increase as you get more felsic. So the overall proportions of that stuff, so discounting mainly the magnesium and the iron, we're going to increase in particular the aluminum, calcium, silicon, sodium, and potassium. Okay, because remember this olivine up here, that has a silicon to oxygen ratio of 1:4 in its structure. We go all the way down to silicon, to oxygen of 1:2 in quartz, which is the bottom of Bowen's reaction series. Okay, that's a lot of thinking in just those two little figures. I will, I swear, put those answers up. That's my task for tonight. Oops. Okay? So volcanoes. Volcanoes are actually pretty cool. This is the stuff after the material in these slides, and these are all the slides for this week. The first bit is about volcanoes. So being able to talk about the controls on how a volcano or how volcanic activity behaves. Is it Hawaii type where you can walk away from it, or is it Vesuvius type where tens of thousands of people die? You'll be able to list and actually describe the 3 different products that happen in a volcanic activity event. The shapes, describe the shapes, or at least list the shapes on volcanoes and what controls that. That'll be linked to the composition. And then at the end, we'll talk about the tectonic setting of igneous activity in general, both intrusive and extrusive, and also the sorts of rocks that you end up with that are characteristic of those settings. What do I mean like that? I mean that I hope that when you walk away from this course, you'll always think mid-ocean ridges, basalt, and that will always stick in your mind. That is the rock type that's characteristic of a mid-ocean ridge. I just threw these out because there are a couple of little facts, and I just think this is amazing about the eruption of Mount Vesuvius. And the pyroclastic flows, that's one of the products and one of the more deadly products of volcanic eruptions that are these hot, gaseous, it's like when you open the oven. If you're cooking, I've got this chicken dish I make that's got a lot of wine in it and olive oil and spices, and it kind of simmers in that. And you open up that and it's not covered. You open up the oven and you just get hit by this gaseous mass of material. It kind of doesn't burn you, but it feels like it could. That's kind of like a pyroclastic flow. But then throw in a bunch of dust in there and ash that you suck into your lungs and you can't breathe. It must have been painful, painful death. Just for example, that dog that got kind of frozen into a very painful position. Must have been terrible deaths. So yes, volcanoes can be incredibly horrible. We talked about the idea there could be one going off now, that could be the end of all human life as we know it. So, as far as the nature or how a volcanic eruption, and I don't always want to use the word volcano, because that makes you think, if I just said, let me just draw up the document camera. In fact, I'll get you to do it. On the back of your crossword puzzle, or some piece of paper, it doesn't matter where you do it. Everybody draw a volcano. I'm going to draw a volcano. So if somebody said draw a volcano, and I weren't thinking like a geologist, something like that. That's what you think of when you think of a volcano. And fair enough. That is the classic composite volcano type. That's the type that's produced by intermediate to felsic magmas, lavas on continental and oceanic arcs. So that's a classic volcano. But this diagram, so I try to stay away from the word volcano and talk about volcanic eruptions, because the floors of the oceans along the mid-ocean ridges are not covered with big composite volcanoes running up and down the length of the oceans. Those are more like fissure eruptions. It wells up into those splitting fragments and just kind of exudes out onto the ocean floor. And all sorts of mafic volcanic activity is not like Dante's Peak type crazy volcanoes rising up out of nowhere. So I try to use the word volcanic eruptions, not volcanoes. The three main factors that control volcanic eruptions are all stuff that you kind of know about already. The magma's composition, so by that I mean words like, is it mafic or is it felsic? What's the next one? The magma's temperature. Is it a high temperature or a low temperature magma? And then finally, the amount of gas that's trapped in that magma as it's on its way up to extrude as an extrusive mass. So those are the three things that are going to link together to give us the different sorts of volcanic shapes that we're going to look at. Oops. So this is just a picture of the three types of, or the three products of volcanic activity. A great image of lava pouring out of these, I'm not even sure where the source of that is. This is old lava, so this must just be flowing underneath it. This is volcanic gases, and this is the pyroclastic debris. That must have been Mount St. Helens, I reckon. I nicked that off the USGS website. So, lava, pyroclastic eruption material, and gases are the three products of volcanoes that we want to talk about. And there are just the words that are describing those three different settings. So the difference between the pyroclastic debris and the lava flows are that the debris is just really stuff, fragments that are actually blown out of the volcano and go into the atmosphere before they fall to the ground and accumulate. Lava flows are actually sheets of molten rock that move over the ground before they solidify. But there's a lot of mix-up of those sort of, what do I want to say? There's a lot of ambiguity about whether ancient volcanic rocks that are seen now are actually lava flows or ashes that have fallen and settled, or some combination of the two. There's a word that volcanologists use that's volcanoclastic. That's when they can't quite decide if the rock they're looking at is volcanic in its origin or sedimentary in the sense that it flowed with water or was carried by currents. But for our practical purposes, just to have this idea that lava can flow, violent eruptions can throw material into the atmosphere, and then also that vapor and aerosols exit volcanic activity. See there, I used the word volcano, and I should say volcanic activity. Now, there's two main types of eruptions, effusive and explosive. I don't like that word effusive. Just think quiet eruptions versus explosive eruptions. Technically, though, it's effusive. These are sort of two end members, effusive and explosive. Effusive eruptions, that's the kind of eruption you get if you have mafic magma. So it starts out low silica, high in magnesium and iron, a dark lava, relatively low gas content. We talked about the idea that mafic magmas that that have low silicon to oxygen ratios, so they don't polymerize as much. They can form isolated silica tetrahedra that don't really link together inside that viscous material. So gas content is low to start with in a mafic magma, but gas content is easily able to escape from a less viscous magma. And this is a low viscosity magma. These are just a couple of images. There's, you'd hardly call that really a volcano, but you can just see the mafic lava just sort of quietly coming out of that. You can envision you could run away from that. Those are some textures of the lava after it cools. Vesicular to massive lava flows. How are we doing? We're doing fine. Explosive. This is mainly with intermediate to felsic material, okay? Not mafic, but intermediate to felsic. Just sort of like, let me just see my next slide. Yeah, okay, we just want to get up to that. So this is driven by degassing of the lava or the magma as it starts to rise up the neck of the volcanic event, this idea of really explosive eruptions. Felsic magmas tend to have more gases to start with by nature of the process of the partial melting that created them from the rock that they were sourced from. So you might get intermediate to felsic magmas by underneath a volcanic arc where you hydrate the mantle, you melt that, it emplaces into the crust and melts part of the crust and continues on as a fairly felsic magma. That's going to have more gases in it to start with than a mafic magma, but also those gases are trapped as that magma is moving up the neck of a volcanic vent. So what happens is basically you get to the point where the pressure on the gas is less than the surrounding pressure of the volcanic vent, and the thing just explodes. That's what happened in Mount St. Helens. That's what is happening that prevents people from traveling to Bali. We have this really basically a captive audience of gases inside these felsic magmas. So yes, this is what creates these pyroclastic deposits that we'll talk about a bit. In terms of lava flow, again, just to think of the type of lava flow related to the magma composition. So you know that magma compositions vary mainly by silica content. That's the thing that controls the viscosity, whether it flows easily or has high viscosity and flows very poorly. So high silica, these numbers are weight percent silica. High silica lavas, like rhyolitic ones, are explosive eruptions. Low silica magmas, like you would find in basaltic lavas, are more mellow, more quiet eruptions. Okay? So we might talk about this whole issue of viscosity and gas content one more time. Okay, we'll stop there and we'll pick up on Wednesday, starting off with lava flows and basalts and the structure of the oceanic floor. That's a good place to quit.